In Module 3, we went in depth on human-in-the-loop workflows. We talked about 3 popular use cases, including human approval of certain actions for an agent, like tool use, debugging through things like time travel, where you can go back and replay or fork prior states, and also editing state. So we're actually going to move now into a new module that ties together these themes with a few other ones related to controllability and multi-agent workflows. And we're going to kind of build all this into a pretty interesting multi-agent research assistant that will kind of tie together all the aspects of the course. Now to start, we're going to talk about a few controllability topics, and let's start with parallelization. So the main idea here is fanning in and fanning out is something that we often want to do in graphs. I'm just going to define a really simple graph here. Okay, this is something we've kind of looked at before. Here's just a linear flow, A, B, C, D, right? I have a single state key, and if I run this, what happens? Okay, so as we go from A, B to C to D, we just overwrite the state at each node. So that's fine, that's simple, and we've talked about that a little bit before. Now let's say we actually want to run, for example, B and C in the same step. Let's just go ahead and build a graph that does that, and all we have to do is just create an edge from A to B and A to C, and that's it. And then B to D, C to D, D to end. So this is actually doing fan in and fan out in the sense that we are fanning out. Let's just draw it out to show you. We're fanning out from A. So we're running A as a step. We're running B and C together in the same step of the graph. And we're running D as a third step. So let's go ahead and try to run this. And I'm actually going to catch any potential errors to highlight something interesting to you. So you're going to see an error occurred at key state. Can only receive one value per step. So what's happening is B and C are both trying to update state in the same step, which is ambiguous. If you think about it, both B and C, think about it simultaneously, are writing to the same channel or same key in the state. So the graph doesn't know which one to actually keep or use. So this brings up an important point about parallelization, which is that if you're running certain nodes in the same step, i.e. in parallel, and they're writing to the same channel or key, you need to use a reducer that can aggregate those updates. And we talked a lot about custom reducers. We talked a lot about reducers in general. So let's just do something simple. Let's just define state with a reducer that will just add updates to a list. And now we're going to draw that same graph. Here we go. So we're going to fan out. We'll fan back in. So now nodes B and C will be updating this state key. But because we have a reducer, all these state updates will just be appended to the list. So let's give this a shot and make sure it works. Very nice. So we can see we just get this list of elements, and we're able to run steps B and C in parallel because even though they're writing to the same channel or key, we have a reducer that handles those updates and just appends them to the list. So the key point to remember is when you're doing parallel node operations and you're writing to the same key or channel in your state, just be very careful and make sure you're using a reducer that can actually handle those simultaneous updates. Now let's walk through another common architecture in parallelization. We'll go ahead and draw a graph out here. We'll modify it slightly. We're going to show 2 branches here. Now one branch has 2 steps and the other only has 1. So what's going to happen? What you're going to see is that even though steps B and C will be run roughly at the same time, that is, they're the first step in each branch, we will wait to run D until everything in this other branch is completed. Now let's go ahead and see that right now. Nice. So we can look at the final state list, and what we can see is first A writes to state, then B writes to state, then C writes to state, and then B2 writes to state. So even though we ran C, we don't go ahead and run D. We wait for everything in this other branch to finish because these are all run, that is B, B2, and C are all run as part of the same overall step. Okay, so you get B, C, and B2 all updated before D updates the state. So it's just an important point to remember that when you have parallelization, these parallel branches of your graph are run as part of the same step, and we will wait until they all finish before running D when they fan back into. So let's look at the state after our graph ran. We have A, B, C, B2, and then D. So you might ask, well, why is C coming before B2? Okay, they run as part of the same step. So you can see B here, C here, B2 here. And the answer is, this order of updates is actually set by the graph. So LangGraph decides how to order these updates when they're within the same step. You don't have control over that. But what if you want to customize that? So we can do that pretty easily using a custom reducer. Let's define a reducer that's actually just going to sort the values in our state after each update. So it's pretty simple here. You can see we basically perform the concatenation, and then we just sort the values in the list. So it's pretty simple. So recall the ordering above was B, C, then B2. And now we're going to define that same graph. Cool. Let's run it. And now you can see A, B, B2, C, D, because our reducer actually sorts the values as they're added. So even though by default we don't have the ability to control the ordering of these updates within the same step here, we do if we supply a reducer that will control or manage the order of those updates as we make them in the state value. So let's pull all these threads together into a realistic example, which we're actually going to end up using a bit later as well. So it's kind of a nice little precursor. So I'm going to define an LM. I'll use OpenAI just like we've been before, but of course you can use any model you care about. I'm going to define a really simple graph here. So here's my state. It's going to have question, answer, and then context. So you're going to see context is a list, and I have this add operator, which means we're going to append to it, okay? So this gives you a clue that this context thing is probably what I'm going to be writing to in my parallel nodes. So that's just a nice little hint you can see there. So I'm going to define two different search tools. I'm going to define a search web tool. I'll use Tavily Search for that. So this is a very useful search service. You set your Tavily API key, and then you can use it. And what we're going to do is hit Tavily with a question that's in our graph state, get docs back, and we're just going to format them in kind of a nice way and write them back to state context. We're writing it back as a list because, again, we look at our key and it's a list. So there we go. We'll do the same thing with Wikipedia. Again, we'll just define this Wikipedia loader. We'll call it with question, and then we'll format the output, write it to context. So you can see these two nodes are going to write to the same key in our state. And that's fine because our key has a reducer. And we're going to run these in parallel. Then we're going to pass it to answer, which will take the context and answer a question based upon the context. Let's draw our graph out here. So there we go. We start, we search the web, we search Wikipedia, we do those in parallel. We write both of those results to the same context key like we talked about. And then our answer generation grabs from context, grabs the question, formats a prompt with those, passes it to an LLM right here, gets an answer, writes that answer back out to state. So I can run it pretty easily. Let's ask a question about NVIDIA, the GPU company, and we can see the result. So this is a good practical use case for parallelization. For example, you want to retrieve information from multiple sources and aggregate it in a particular key, in this case context, and use that later for answer generation using an LLM. So let's interact with this graph using the LangGraph API. We have our graph with parallelization deployed to Studio locally. We can interact with it via the SDK. Just apply the URL and the assistant ID. So we pass in a question just like before. we create a new thread. And if you recall, each event we run stream has this data object, which is just the state. So all we're going to do is, as we're iterating through our graph and it's producing state updates, let's just go ahead and get answer, and we'll only return answer. That's really all we care about, right? We're not going to return intermediate updates. So we could, of course, we add to context here, for example. We could print those, but let's just print the final answer in this particular case. We run it, and there's our answer. So we can also look at this in Studio to see some of those intermediate outputs. So now we're in Studio, we can see our graph here. Let's just open up our inputs. Let's just go ahead and ask a question. How are NVIDIA 2024 earnings? Let's have a look. So now we can see we're going to each of our sources, doing web search, and we're searching Wikipedia. And this is pretty cool. So we get a whole bunch of information in our contexts, and we get our final answer.